here's a news flash for you. Mel doesn't need my help.
I absolutely adore Doc. He's brilliant, he's clever, he cracks me up every time he speaks. He's charming, and I swear to God, if you are gonna scorn like a Scotsman.
Have you seen any of her videos? Or is this just a thing that you're trying to do this divide and conquer, that Mel needs my help because I have testicles for some reason?
Do that. Hey guys, welcome to the 16th episode of Oral Audacity. And today we have Landon Noll. And also, it was Doc's birthday this week, so be sure to tell him happy birthday in the chat.
Thank you very, very much. I'm officially older than Dumbledore. This is my 5th regeneration. This body's getting a little bit wobbly. It's holding up mostly. I may have to transition soon and become another mortal form. But thus far, all good, and thank you for your kind wishes.
All right. Well, Landon Noll, it's super awesome to have you on the show, and thank you for joining us. Why don't you tell everybody a little bit about yourself, who you are, what you do, what you love, all of that.
Well, good morning, good afternoon, or good evening, depending on your time zone and latitude, and perhaps even attitude. They're from. I'm Landon Noll, your friendly secular astronomer. And by the way, congratulations on show number 2 to the 4th, right? And that's it's a nice. You got to go away to get to the next there. 4th power.
So what you did there. Mathematical punning. That's the kind of people we have on this show.
I must admit, as you were saying, 60 was like one short of Fermat Prime, right? But you'll get there, right? Hopefully, the show will survive this session. And so I'm an astronomer, a mathematician. I'm more specifically, I'm a planetary scientist. So we study planets. I mean, don't get me wrong. Galaxies and stars are pretty interesting objects. But it seems like part of their function in the universe is to create planets for us to study. So, and particularly, so my colleague called me a nearsighted astronomer, right? Because typically we only see planets that are like nearby, and my cosmologist friends look at stuff on the edge of the visible edge of the universe.
Nearby in astronomical scale. So perhaps you could elaborate on that briefly for the audience.
Well, I mean, if you consider the most of the planets that we know about are around stars within a few hundred light years of Earth, that's pretty nearby. So in other words, it traveling at the speed of light, 300,000 kilometers a second, it took light somewhere on the order of let's say up to 1,000 years. Now, astronomers deal with other galaxies. I mean, you're talking about in the millions of light years, and when you talk about stuff in the Big Bang cosmology, you're doing well over in the many billions of light years, depending on what you're looking for. And of course, it depends on whether or not you're talking about the size it is now or the size that it took light to reach us.
And the words of Douglas Adams, peace be upon him, ring, I think, through all of our minds at this point. One thing that most people don't get about the universe is that it's big. It's really big. Imagine the
really big.
So big that it will fry your brain. And I can really understand some of the attractions of the flat earthers who think the circle that they can see is what is, and object permanence is a distant concept for them.
Yeah.
Well, to be honest, when I was I was about 22 months old, so just shy of 2 years. I uttered the very first complete sentence, and my very first complete sentence I uttered was, "How far is the sun?" Right, and that I guess that sort of had a portent of dealing with wanting to explore my favorite universe. But I have to tell you why I asked that question of my parents. We were sitting in our farm, which was located between the cities of Hayward, California, and Pleasanton, California, sort of up on the ridge line. We were overlooking the Bay Area, and it was an evening. I was watching the sun set over what within is the peninsula that San Francisco is on the end of. And I was watching the sun set over there, and was thinking, if the sun isn't too far, maybe we can go and visit, because I did not believe the Earth was flat. I believe the Earth was lumpy, because I could see lumps, right? It wasn't. I'd heard people talk about flat stuff, but that seemed absurd because I was on a hill and there was lumps, right? But I thought what I could see was the edge, and if it wasn't too far, we could go over to that peninsula and watch, the sun go over. And of course, they brought out a book. I still have the book in my library. It's called Questions Children Ask. And it went through the page, because apparently how far is the sun is one of those questions. And they had this, in the United States, we have these interstate highway signs, right? That talk about distance to sun, brother, and exit. So there was a highway sign, and it said sun, and we weren't, it was miles then, and it said 93 million miles, pointing off toward the sun. And I looked at that, and that seemed a little bit too far to measure. Right? I knew a mile was 5,280 feet. I don't know why I knew that, but I knew that. And on our farm, the largest tape measure we had was 100 feet. And I knew that going to grandma's house was an all-day affair, 515 miles away. And I figured you could take that tape measure and go for 515 miles and find it, right? But 93 million just seems too far for a tape measure, right? And so I had this moment of crisis. So my second sentence, since I spoke as a child, was a one-word sentence: why? And that's how my science career started. But I wasn't a pure flat earther. I was at 22 months. I was Earth is lumpy, and I quickly figured out a more accurate version of the cosmos, and cured myself of that.
Mine was very similar. At a similar age, I refused to believe in elephants until I saw one with my own eyes. My mother would show me these pictures in books, because TV was a thing, but you couldn't just go, here's an elephant, you couldn't pull up video of it. And I'm like, no, you're shitting me, mother. No way. And all credit to my parents. They were like, right, we have a perfectly good zoo. And my life was transformed.
Wow.
And there's an elephant.
So you saw your first elephant. Did the elephant appear based upon, did it live up to this description, or was it drawing and so forth?
It was astonishing. It was the description and 10 times more, because I was 2 feet 8 inches tall, and you at that age, you could get quite up close, and I was just astonished by it. Rhinoceros as well. It's like, wow.
Have you ever? How long before you actually touched one? Right. That's another.
I actually milked an elephant on one occasion, because I used to work on a protein called lactoferrin, and before we could synthesize shit, we had to go like, okay, Mrs. Elephant. And the keeper was like, you have to talk to her before you do that. I'm just like, well, I would expect to. And it was
whispers.
My hands might be cold.
Grab her, and it was a lovely experience.
Did the elephant consent to the milking, Doc?
Well, it's difficult to know. She could have stomped me into jelly if it was an issue. And it was for science.
At least you knew it was a female elephant, right? It'd have been more.
Oh, I definitely did. Yeah, I'm good that way with the biology thing,
The first time I had to do a neutering a cat, right? You gotta have cats. We had cats on the farm. They were working animals, and one of the things I expected was take care of the cats. And one of the things in particular is you do your neutering. And so I had to learn how to properly anesthetize a cat that took a dim view of being poked. And it was part of the learning exercise. And I eventually kind of I had parental guidance, but they were sort of figured out. Eventually, after a struggle, I did the right. You basically put the cat in a beach towel and you roll the thing up, and it kind of minimizes the cat's ability to do
They
stuff.
just
And then
resign
you
after a
find the
while.
vein and and they actually they start purring, right? Which also sign of nervous. And then you inject the vein with a random thing to sort of anesthetize them, and you turn over and you say, it doesn't have the thingy and it has the other thingy. And they said, did you bother sexing the cat before you decided to neuter it? So I had to learn how to do spading, right?
I mean, the one disadvantage of the wrapping the cat strategy, which is generally good, is have you ever tried to get cat shit off a beach towel? Because they do chemical warfare.
Yes,
and
yes.
they're vengeful and they don't care.
Yes. So people wonder, so how did you end up with physics and computers and astronomy growing up on a farm, and it's things like this, these experiences that scarred me for life, unfortunately, in the biological sector. I mean, probably the worst one was that I had the smallest hands. And the smallest hands meant we waste wool is one of the things on the farm. And when there's a breached lamb, the smallest hands must go up inside the uterus and twist the lamb around so it can come out in both. And this is not something that, unless you're predisposed to become a vet, is not something that a 9-year-old thinks is fun.
Oh no, a 9-year-old. That's too young. No, unless
you learned a lot that day.
Did you give consent? I mean, was this a thing you did? Did you do it willingly? Because I had a similar upbringing and I loved that stuff.
Well, I mean, I didn't. I guess it was probably they didn't have quite the, if the parents may have had a different approach towards things, and more guiding stuff, I might have taken a shine to it. But by the way, the lamb and the lived. They survived. I didn't survive it very well, but that's when I discovered you could press buttons. You can do equations on the board, and to me, physics. Why do you want to be a physicist? I said because it's clean. And I was an egg production was my thing, and so I probably cleaned well over somewhere between 1.5 and 1.75 million eggs of chicken poop, because most city slickers don't know that the eggs come out near the same thing that produces pernicious amounts of Mr. Hanky. And so all those things to say, why did you become an astronomer or physicist? Because of experiences like this on the farm.
I mean, conversely, I became a biologist because I love all that stuff. It's like, and how does stuff rot? What happens when it dies? What does it turn into? Why does all of it happen?
I thoroughly enjoy it, and a lot of respect for biology, for genetics, and all that sort of thing. And when I go on site on an expedition, astronomical expedition, let's say in Africa, I always try to find a guide who's a botanist, because I figure the botanist knows, what the birds are, and they can say, giraffe, elephant, blah, blah, blah. But they also know all the cool little plants and bugs and things down in the thickets where most people ignore. And there's amazing colonies of critters down there. So So yes,
Um,
I thoroughly enjoy it. I just that early trauma on life, learning about the sun being really far and then all the squishy stuff.
Yeah.
Again,
well,
highest level of respect
I
for that.
I have a very, very long reach and grew up in cattle country to a limited degree. Go on,
Yeah.
son, get in there. I was told by a lovely vet, there's more to be learned up a cow's arse and many an encyclopedia. While I
Well,
was
that sounds,
show,
man, that sounds like a campaign slogan.
you're probably right, but I'm not convinced at this moment. But you know what? Yeah,
So,
I sit in an office and tell excellent scientists what I'd like them to do, and they do it, and I don't get my hands dirty anymore. But yeah, it sounds like we've had, is it common path, different result, common path.
and I was expressing how, I would find it amazing that you can take gene sequence and tell me a bee and a beetle had a common ancestor and how far back that was. And I find that
Yeah.
utterly astonishing. And his reply was, I find it astonishing that you can take 17 photons and tell me the age of a star that you can't even touch. So it's
And the mass of it, and
and the
conceivable,
temperature.
Yes.
I mean, I explained spectroscopy to my mum, who was educated in the 1950s, worked as a nurse, no advanced science, and it changed her life. It's like, we know what this is made of because of these things. Wow, that's cool. But for
And the fact that we
astronomy,
can now look at a spectrum of a star and discover planets orbiting that star through the spectrum. It's amazing what we do. And we're going to get these new telescopes. I hope the James Webb Telescope works, because we're going to be able to do direct near infrared and mid infrared imaging of atmospheres of planets around nearby stars. We'll be able to
that'll be
see
all based on spec.
Yeah, and to see the interesting chemistry going on that's being generated by lightning on a planet orbiting a star way out there.
Yes.
That's the next generation stuff that's gonna amaze us.
See, I'm very excited about that sort of thing, particularly with Titan, getting more information from Titan. I had a completely different beginning than you guys did. I'm in academia now, chemistry. So it's just like I'm dealing with all the budding folks that are coming up from the fold to be welcomed into the science world. So but I'm all in chemistry, but it's always fascinating to be able to discuss spectroscopy with the next group, because a lot of them don't know that that's a thing. And so when you explain that to them,
it's
amazing.
It's super cool.
And then when you have something like you see, it's one thing to do and try to get analyze stuff as on a spectrogram of an object in your lab, but now put it on something where it's been Doppler shifted way down and stretched and squished, and then you've got all these absorption lines, emission lines, other messy things in the middle of it, and it becomes extraordinary because the chemistry out in outer space is weird. And it is almost impossible to even come close to replicating the slightly near conditions of that sort of stuff, right? Having the extreme vacuum of space, 500 million years and a magnetic field can do amazing stuff to atoms that are very
radiation
difficult to comprehend.
Spraying around everywhere. Antimatter fountains. Yeah, I mean, a lot of stuff can go on there. So
gravity's
that's going to be
a little bit, So
one of the things that one of the experiments that I'm looking forward to, the James Webb, and that's the successor to the Hubble telescope, coming forward,
Mhm.
is that there's a program called Starshade. It is very difficult to image planets uh, in other than the ones around our star, next to nearby stars, because the stars are so bright compared to the planet, right? And you've got things where you might have 40 stellar magnitude difference between the brightness of a planet and brightness of a star, and they're right next to each other, right on top of each other. So it's sort of like trying to it's trying to read the name of a maker of a searchlight beam, where the searchlight beam is pointing at you. Right? It's very, very difficult. And so there's a thing called Starshade. One of the things is that it'll be basically these. Think of like an umbrella, right? It looks sort of like a daisy petal umbrella. And this object is going to fly in a very specific, they'll fly in a very specific path. And they will be, let's say, several million kilometers from the telescope, but pass directly in front of a star at a time where we know there's at least a planet orbiting, right? How? Because we see the spectrum shifting back and forth because of the tug of stuff. So we know which side it's going to be on. And when this shade blocks the starlight, the star blinks out or occults, and then the telescope can directly image the planet. And not only that, but you're out in outer space. So you don't have all this water vapor and other stuff messing up your spectral things, and we'll be able to do direct spectral measurements of the atmosphere. And so right now we're trying to figure out what's the first targets, because it's it's kind of a shot, an orbiting shot of getting that thing in there. They're a bit expensive. So the question is, well, what do you pick your first targets for? And again, I'm hoping that our first targets are going to be things that have really weird chemistry, right? I don't want something to sit there and say, yeah, okay, here's some hydrogen, helium, and a little bit of methane, or ammonia or something. I want long, weird molecules and spectrums that's really messy. And
Yeah, man.
Go
big on the molecules, and keep your eyes open. Just for me, just keep this as a thought. Keep your eyes open for the very characteristic spectral shifts associated with photosynthetic pigments.
Exactly. That'd be cool.
I mean, I know that we're at that stage in some of the moons of Jupiter, because they're essentially next door, but still really difficult to image. And can I draw you into that? I'm hoping to live long enough to see probe data direct from Europa or Titan.
Yes, because that's one of my I'm pushing there. I mean, I know that they're sort of people have their favorite missions, but I think your understanding Europa and the composition is going to be very, very, very important. If I had to put bets on saying, okay, let's presume there's life in the solar system, not on Earth, and not in one of our little space pods, where would it be? One of my strong bets would be Europa. Another one might be Mars. Right. And there's a few other spots there. Yeah. So I mean, the European Space Agency joint mission, the next Europa Pathfinder mission, is to try and understand, is Europa a good, well, I guess for the audience, we should say, why is Europa unusual?
Yeah.
Right. What's unusual? Right. And I remember, it was I think it was one of the Pioneer missions, and that got our first image of Europa. Yep. And I remember saying, where are the craters? Right. I'm so used to the moon, right? Our moon, right? Pockmarked spots on there because you don't have an atmosphere to wash things out. And I saw this almost perfectly smooth body, about the size of our moon. I mean, it's comparable in size, maybe like a few percent.
And what does that suggest to you directly that the layman might not come up with?
You have to go a scientific thing. You have to say saying either this thing is brand new, right? A baby moon, which would be weird. How could it form, and where are the telltale signs of its formation? Or it's been incredibly lucky in missing stuff, which seems to be highly improbable given its potential age, or there's some process that affects the surface that is important. Well, it turns out it's that third thing. Europa has an enormous ocean. It's the mass of water, we believe, is about 6 times the mass of Earth's oceans. So something about the size of the moon has 6 times the mass of water on it, than Earth. It also has a magnetic field. Because this is a surprise. We say, well, magnetic fields only come from the really bigger planets that have the inner core dynamo and so forth.
Yeah,
so the fact that this thing has a core, has a magnetic field, which of course immediately says, wow, now you've got something that can shield it from the fairly inhospitable environment Jupiter. Jupiter has a really, really, really nasty radiation problem, right? It's got these enormous magnetic fields and high energy particles, so forth. You do not want to go and visit Jupiter close up. Just bad news, right? It's like
I'm hearing the layman question again, and it's a valid one. So it's a long way from the sun. It's spinning around in this very inhospitable environment. How can there be an ocean, albeit an ocean under ice?
Yeah, because you would expect this thing to be frozen over, right? And to be this frozen ball of ice. And then when things hit it, you'd expect the pock marks, the craters to stand there. So so it's not. How is it possible to be that cold out in space and yet have liquid water? And one of the answers is tides. This moon has enormous tides, and our current estimates of the tides are somewhere around 500 meters high. So it's about 1,600 feet for those that are metrically challenged, and twice 80.
I love
every
metrically
80.
challenged. I'm sorry. Let me just say, I'm going to steal that. I hope it's all right.
That's fine.
Well,
okay, please.
I know pounds, shillings, pence, pounds, ounces, kilograms, meters, and so on. So I guess that means I'm transsexual, right?
Yeah, but I did also, just to say, if you're going to do odd units, when I go to physical therapy and have to do, part of the thing is I have to weigh myself in my birthday suit. I come out and announce myself in stone, pound, ounce.
Yeah, stones. Yeah,
stones.
but back.
That
So
goes
the
back
fact to
to
say
the ancient technologies of the Scots, where
absolutely. Absolutely.
They still use stones though when they talk about weight loss. I see it on my Twitter. I lost 2 stone, guys, and I'm like 28 pounds. All right.
Wow.
Yeah, that's a lot. Good job.
But Europa has a water ice, or has a water ocean, because tidal things cause energy transfer. So gravitation can actually do the warming bit. It's awesome.
Yeah.
And it actually goes to say that there are 3 of the 4 big moons around Jupiter. Jupiter has lots of moons. Currently it's only 79, and we know more on Saturn, but Jupiter will catch up. We'll find some more. But anyway, of Jupiter's mini moons, the 4 so-called Galilean moons are the big heavyweights. Right? If you Io, Europa, Ganymede, Callisto are the 4 big. And if you see, even in a moderate sized telescope, little spyglass thing, you can see Jupiter and a couple of the moons around it.
Can I chime in briefly?
Sure.
Can I chime in briefly for the flat earthers? They're called the Galilean moons because they were discovered by a guy a long time ago, looking through a thing, not at a crystal dome and firmament and all the nonsense that you believe. No, a smart guy a long time ago.
Oh,
and I'm seeding the conversation intentionally with flat Earth just to kind of draw you into that absurdity.
Sure. But also, there also was the Galilean moons. Moons were also co-discovered by another gentleman, and the Galileo had a really sort of a lifelong feud as to who was, who discovered the moons there. So, what does I say? It was Galileo sort of that certainly it was quite well known and popularized it at the time. But Marius, Marius, Simon Marius, discovered the moons within a couple of days of Galileo discovering them. So he wasn't the only person using optics to look at stuff. And
this sounds a bit like Crick and Franklin.
Exactly.
Sounds a little bit like Rosalind Franklin and Crick and Watson.
If any smart people are looking at an interesting problem, they're going to approach it in different ways and pretty much come up with essentially the same thing.
Yeah. So our names, Io, Ganymede, Callisto, Galileo, are from Marius. Galileo would have named after his benefactors, the Medici brothers. But,
and it's Starbucks.
Whenever you guys get a moment, I do have some questions from the chat, but please finish. Please continue.
So let's finish. I'd say so. These four big moons are the heavyweights. If you looked at the fifth largest moon around Jupiter that we know of, it's like 1/7,000th the mass of one of the Galilean moons. So the Galilean moons are the big heavyweights. And Newton, he talked about his law of gravity, and he described orbits and orbital mechanics. But in observing the moons, particularly Io, Europa, and Ganymede, they started doing a very weird thing. There's a thing now we call it Laplace resonance, where every time Io goes around 4 times, Europa goes around twice, and Ganymede goes around once. That 1 to 2 to 4 ratio, the very solid ratio. Moreover, they're in a phase where when you get 2 of the 3 moons on one side, the third moon is always at sort of like a right angle with respect to Jupiter. That's important back to our thing about looking for life, because that's what's called an orbital resonance, right? If you've ever tried to dry your bed sheets in a tumbling clothes dryer, and you get that ball of stuff on one side, and it starts to oscillate, and the clothes dryer starts to wobble around on the floor and so forth. Well, that kind of resonance happens with planets as well. And
I have an example.
Good.
Have a liter of solution fail in a fast centrifuge, and it's frightening. The thing coming off. It looks like something from The Exorcist.
Yes,
I can completely relate to that, and it was horrifying.
So that energy, what energy does is it causes the orbits, which should be fairly circular, to become somewhat elliptical, and because the moon's going to tug on each other, and that elliptical orbit causes very interesting tidal forces to exert on there, because now the moon is moving closer and farther away, within like a percent or so of Jupiter, and so it gets a bigger tug, a smaller tug. I mean, it's so severe that Io is the most volcanic body that we know of, because it's basically being stretched enormous. There's the study I helped do. We calculated that Io has around 93,000 gigawatts of thermal power just coming from the tidal forces. 93,000 gigawatts is a lot of stuff. Moreover, because it has a lot of sulfur in there, you have this semiconductor moving through enormous magnetic field of Jupiter, and so you've got this current on the order of trillions of amperes going between the two, and it's so no wonder it's and so Io is a bit too close and it gets too heated, but Europa is a little bit farther back, and it also is this tidal flexing, and the result is it has enough tidal thermal energy to maintain water in a liquid state. The question is it an eggshell model where you've got a very thin crust and nice, water underneath, or is it more like a slushy you might find at a soda fountain, right? Is it a snow slushy, or is it a thin crust and water underneath?
Yeah.
And we'll find out, because that's the reasons to go there and see if there's interesting chemistry going on inside there.
I want to know if I want to know if there's any internal hydrothermal activity as well. If there is,
Yeah, I mean,
I'm at the point of saying I would be surprised if there wasn't something crawling around there, provided
some kind of a
temperature's enough.
chemophile bacteria, you would think. I mean,
and
chemophile
it's got a
bacteria would
very
be a thing.
yes,
provided
very complex
the
tides in
planetary
there as
body's
well.
been there for 2 billion years.
Sure.
3, even better.
So you have a
life
nice
is
magnetic
an
field that's
emergent
going to shield you from some radiation, but not all. So now you have radiation comes and scrambles the chemistry around on there, and I mean that's part of all the recipes that say, can the chemistry do something interesting? I have to say, the chemistry I tended to enjoy was the physical chemistry stuff. So
physical chemistry is fun.
It is, and doing things like, for example, even do something simple as like separating hydrogen from deuterium, or another one of my things was to take a cubic meter of dirt from the construction site next to the lab and go through and try to extract as much thorium out of it as I could, and I got within I was able to extract about 8% of the thorium that should have been there.
So I have a question.
I do that with gold, but
you do that with gold. So I have some questions from the chat for you, but I also have a question for you. Speaking on the lines of physical chemistry, one of the things that they required me to do for undergrad and also in grad school was Touchstone of Life by Lowenstein. It touches a bit on information theory as it is in regard to biological systems, and they talk a bit on Maxwell's demon. And so it's really just kind of a neat book on how information theory plays a role in genetic code, biological systems, that sort of thing. So I didn't know if you've ever read that book, but that was something that was required in our physical chemistry class, which I thought was kind of a nice little touch for, a bit of that understanding how. Mm-hmm.
I've only read the reviews of it. Sorry, but it is a fascinating question, which is really, because it talked about, I remember the parts I did read, talked on the physical processes in biological systems, right? It's fascinating sat there. So when I was involved, doing some work in radiation oncology, I had to study a little bit more about cells and understand a little bit more of the chemistry of stuff. But still, it was a physical thing of shooting high energy particles through a fairly complex chemical system there. And so yeah, cells are amazing, right? They're extraordinarily complex things.
We've got a physics question for you. Sorry, Doc. What were you going to say?
No, carry on. Please bring the questions. I'm...
Okay, bring the questions. All right, so we have a couple questions. The first one is for you, Doc. Were you able to milk an elephant without getting personally involved? That's from Steve Bowden.
Yeah, but I was very ethical.
It's very ethical.
But you personally milked an elephant, so there's some involvement. It's not completely sterile.
Yeah. And I spoke to the elephant. She didn't seem to object. She seemed like a very nice elephant, was very calm. And I explained it's for science. We're going to take your lactoferrin. We're going to work out why it kills bugs and cancer cells and whatnot. And thanks, Lady Elephant. It was lovely. It's a really nice experience. And I gave her a bun as well, which she seemed to enjoy. Oh,
goodness. And then Steve Bowden has another question for you, Landon. I have a physics question. When I heard that moons of Jupiter had tidal effects heating their interior, I imagined a moon getting bent repeatedly as the moon spun on its axis. But so I think you kind of explained that a little bit when you were talking about how they kind of shift to that ellipses. So that might have answered that question already.
If the moon was in a circular or very near circular orbit, then the gravitational field it experience would be very much very constant. The problem comes because it gets to be much more complex than the simple tides that we deal with of Earth Moon. One of the things is that the moons are tidally locked, meaning that they have one face that faces towards Jupiter pretty much all the time. But tidal lock doesn't mean they only have one. Actually, a little bit of wobble. We call nutation goes back and forth. And why is there a wobble? Well, if this is Jupiter and you've got an object, a moon going around it, that moon has to change its position, because if it's one face facing there, it means that every time it goes around Jupiter once, it also has to turn on its axis once. Right. So when something's tidally locked, you think of its year and its day effectively are the same. Now the problem is that if you're in an ellipse and you're coming in, it means when an ellipse, if I'll exaggerate there, if your ellipse, the object comes in, it speeds up, zips around, and goes back out and slows down to the edge, right? So it's a zip. So it's not doing constant speed. As it goes in closer, it speeds up and then comes back down and then slows down, climbing out of the gravitational well. But things that spin on the axis want to do it at a constant rate. Well, that's a problem. Yeah. What happens is that object, as it comes in, starts speeding up, and its spin doesn't keep in line with it, and so it actually lags behind. And then as it slows down, it catches up. And so what the object actually does is kind of this back and forth sort of wobble. We see the similar thing on Earth's moons. We actually see about 10 degrees. We don't see 180 degrees. We see about 190 degrees because the moon's kind of sloshing back and forth. That now, combined with the fact that you've got a experimental liquid in the system, and things get really crazy as far as currents and tides and other things. So it actually becomes quite complex. And in fact, one of the things that we discovered was that this 4 to 2 to 1 resonance that the Laplace explained, right? Newton had his Principia Mathematica, but it was Laplace that actually went and corrected it. The most times when people look at Newton's original work, they'll see it Laplace, where he filled in some gaps, he corrected some notation mistakes and other sorts of things, and explained a bunch of stuff. But Laplace's 4 to 2 to 1 resonance turns out to be not permanent; it's slowly breaking, and the question becomes, what happens when it breaks? Well, the orbits are going to become circular. It's going to mean that those volcanoes on Io are going to go dormant, and Io is going to cool down, and Europa also will suffer a fate of its oceans will freeze. What we don't know is, has this happened once before or many times before? Does it cycle back and forth, or we happen to be at the point where Europa is going to experience a freeze? If it freezes, then its chemistry becomes less interesting while it's kind of in a frozen state. So it might not have had as much time to evolve complex chemistries or not. Yeah.
So I'm visualizing the Laplace resonance, the breakdown and reestablishment thereof, as the catastrophic events that may have interrupted or punctuated the chemistry going on and the life as an emergent property thereof. So my qualification
right now, we don't know enough of the fine details of the breaking of the Laplace resonance to have, because we have to use a 117-year baseline of photographs taken at the Paris Observatory back in the late 1800s and comparing the positions now. It's a fairly complex process. And at best, we could say that the Laplace resonance will break somewhere between, we think, 10 to a couple 100 million years from now. And what we don't know is once it breaks, how will it just stay there permanently, or will it reestablish? Because there's another galaxy I haven't mentioned, Callisto, and it is at like 9.4 orbits of Io. But it's possible that Callisto was in a Laplace resonance as well, and it's the first one to break free. So that has profound impacts on the history of Europa as well as its future. So,
well, here's a question for you from Aries 106. He says, "I wonder if Europa is going to alter its orbit as a result of Brexit."
Well, Brexit might cause the former United Kingdom to be less interested in Europa than Europa is in the former United Kingdom. I say former because I can't take the United part serious. Now, I full confession, I have a number of proud ancestors in Edinburgh region who are very proud members of a party called SNP, and they've been trying to figure out how to stick it to the English for several centuries, for the purpose of doing what? So they can stick it to themselves, right? Scotland should have the right to do unto itself what England does to it now.
We have our own fuck-ups. We want them to be in charge.
And that is as egalitarian. But how does Brexit affect Europa? Well, it probably affects the science, right? There's some very significant science going on in those islands off the coast of Europe. One of which, for example, is the Square Kilometre Array. There's an amazing telescope array that's being built in both South Africa and Australia, which is headquartered in that spot. And unfortunately, the scientists that live there in headquarters and are helping, build this marvelous thing, they don't even know whether are they going to be allowed to live? Are they going to be allowed to stay there? And so the impact of Brexit, and I'm not saying because it's a decision, but just understand the impact of Brexit has significant impact on science, where there's a lot of science is cooperation amongst nations.
Yes.
Not just because it's big, but because
Brian Cox is really huge. He's very vocal about how, Brexit is going to affect the state of science in the UK. And he's been very, very vocal about that. Some people are having to pack up and leave now. They're because they haven't had their stay renewed.
I've both been an immigrant in the USA as a scientist with the visa things that, advantages you get. And I'm also an independent consultant in biotech living in mainland Europe, where I can live and work without any restrictions at present. Comparing my experience to someone who requires a European individual country visa and the Schengen type, it's a pain in the balls, and would be expensive and would restrict the number of places that I'm actually able to do my job. So I wouldn't go to those places.
Yeah, and so ignoring whether you think Brexit is or is not a good idea, it has impacts on the free flow of information and science cooperation, and that impact is not a positive impact; it's a negative impact. So, how does Brexit affect Europa? It affects the attention span that the great people that those wonderful islands have on that. It affects science projects that happen to currently be located. But here's something that I think is unfortunate, is that if you were saying, hey, here's a new science project, where should we headquarter it? You can't at this time in good conscience put it in any of the former 4 United Kingdoms, because you don't know the impact of it. Not because they're great places, because again, there's amazing centers of research there, but you just don't want to risk it.
Yeah, I mean, the political veneer over the top of it is an absurdity, and I think of it as kind of parochial politics at the moment, although it is significant, but much less so than the English believe. And you raise a very interesting point. Scotland in no way voted for the present government or the preceding one. The entire country was like, no. So we had a mandate because of a lower population. Scotland has always been an independent country, despite what the Treaty of Arbroath says. Our culture is distinct in exactly the same way as Canadian culture is distinct from Louisiana culture,
Sure.
or
Oh,
French
gosh.
culture from Cornish culture.
Yeah, it's its
Um,
own thing. Yeah.
and
Um,
I'm not a political person, but I support the SNP for one or two reasons. One, Scotland should have an independent government, not the crumbs that we were allowed. Here's some government play toys. Go and pretend to have a government. And the other thing, which is the first manifesto item of the SNP and has been for 25 years, take your nuclear weapons, all of them, and take them the fuck out of my country. There's
oh
nice
gosh.
waterways. You could do that. You can have them down around London. Oh, we'll just put them up in Scotland because those porridge wogs don't really matter because they've got no money. Oh, except for the oil. Oh, and the brilliance. Oh, shit. And the coal.
Yes,
Oh,
yes, yes.
no.
Yeah, in fact, so I one of my when I visited first time I
Sorry.
visited relative relations
got
up
political.
in Edinburgh region. I did an
I
interesting
got
little
political there.
experiment
sure?
on me. They got in my wallet and removed all of the English pounds and replaced them with Scottish pounds. And then they told me this, and it said on the way out, it says, by the way, in case you want, it's Scottish pounds, they're pounds, but we know you're going back to London, the Soho district. We're just interested and curious as to how these spend, right? And I saw the commentary, the stuff. In fact, I was in a pub where this pub owner, I paid for the round of drinks. Pub was raged, who was bringing the Scottish. He said something very nasty there, and they found
Same
I was a
currency,
Yankee. Like,
you
okay,
morons. It's pound
Oh my
sterling.
yes,
It's
goodness.
the same thing, idiots.
but yeah. Anyway,
Yeah.
so back to say about science. It's a very important area of science, and I hope that people can focus on doing positive things rather than doing silly things. I mentioned this because
Yeah.
one of the things also I have to do is analysis. You do analysis of how the Square Comet Array project is going, and it causes me to have to pay attention to the politics in South Africa, Australia, and in
Yes.
House of Commons.
Yeah.
And
Here's
so yes.
as a parallel to that, I'm involved in strategic planning for biotech involving derived stem cells.
Yeah.
And we're looking at America going, can't really do it.
Yeah.
Because of the Bush prehistory and because of the imminent fascism or the incipient fascism. International business, as far as I see it, is viewing the American environment increasingly as a politically unstable one, and one that we're treating with extreme caution when it comes to advanced medical technologies, because religious fundamentalism is a potent political force.
Yeah.
Clearly in this particular administration. I have a question for you guys.
Sure.
So I have some ridiculous videos that
Ooh.
you guys
Those
might
are
want to
let's
make
lighten
fun
the
of.
mood.
Yeah.
Life on
All
Europa, ridiculous shit on the internet. Let's do it.
Yes.
So I thought we could. I've got 4 different riff videos that we can pick from. One is about, I believe it's Alex Jones endorsing flat Earth. There's another one on Bob the Science Guy's Mount Rainier shadow evidence is now flat Earth evidence. I've got that video. I have one on geocentricity, evidence of the stationary Earth. I have another one that talks about how John Quincy Adams used to believe in the mole people of Hollow Earth. And it's a video that's a comedy video where they talk about the history of that. And then I have another one where it's a guy.
Wait, Mel.
What?
Did you say mole people?
Mole
Because
people.
everyone knows the mole people are 100% legit. Because I have them in a book, and it's old. And
Well,
I have faith
Zilch
in the
Fletcher
book about
has a famous song about the mole man, so you know, there
Yes,
must be
that means
something.
it's true.
people
It's
have given their
true.
lives for the mole men.
They have.
Okay.
And then the last video I have is on light speed measured, proving the flat earth experiment from Professor, I think, L.W. Anchor. I think he might be a Poe or a comedian. Not certain if he's serious or not. I can't tell the difference anymore. So I have 4 different videos. Which one would you like to have a go at?
I mean, I'm the two that are tempting, and I'm saying why. So I explain why I'm picking it, because whenever you encounter this thing, I think it's important for people to sort of understand. You know, okay, we poke fun at silliness, but then how do we know, right? So in the case like the light speed, how do we know? How do we measure the speed of light, and how do we know its speed? Is one of the things. The Earth being stationary. How do we know that the
You
Earth
can
is
bounce it
moving,
off,
right?
Professor. You can bounce it off the moon because we put mirrors up there for that exact purpose when we went.
Well, in fact,
there.
I'm one of the people that uses the Shane telescope just in that direction. It's not more than about an hour's drive, a 3-meter telescope, and we bounce a 60 kilowatt laser off of the moon, and we get the position now. The current SAR is around 1 millimeter difference between the two mirrors.
God.
The problem is most of the
Newton.
error is in the Earth being squishy. But anyway, I'm getting all this. So maybe that we could start with that geocentric thing, perhaps. But
Okay.
I'm explaining why, because I think the value is in explaining how we know what we know.
Absolutely.
I
So
have
Bull, the geocentricity video, the
I have
third
a
one in the
short,
folder.
dark socio-political comment to make. I see flat Earth as being it's like the real bottom of the barrel intellectually. In the exclusion chromatography test for intellectual acumen, religious fundamentalists sift out before the flat earthers. If you can convince someone that the Earth's flat because reasons, you can get them to give you money.
Yeah. I wish I didn't
And
have
there's some
morals and ethics because I'd be rich right now. So
dumb like you wouldn't believe. I asked the question in good faith. All right, I sail, and great circle courses and celestial navigation work. Right, they work real goodly.
Mm-hmm.
How's that possible? Because they can only work on a spheroidal surface. They work because ships don't go on land. Oh, brilliant!
So I like to say that I'm the flat earther's worst nightmare, because not only have I measured the distance from the Earth to the Moon, Earth to the Sun, we did it twice with the transit of Venus, and I did it with my good friends in Australia on Parallax Set. I've measured the distance to the nearby planets and stars. I've measured the curvature of the Earth, the size of the Earth, mass, all this stuff. Again, from my old premises, not because part of the process of science is exploring and testing and broking them. So
you can do these
that's
things.
awesome. You can do these things. Bull, have you got the video set up?
Yep.
The geocentricity. Let's have a look at this nonsense. Well, actual real science experiments and stuff, or at least what they say it is. We'll see.
I just know about diseases.
Geocentricity. The hidden scientific evidence.
This is the second improved version,
is
guys.
At the center of the universe.
That's
we
it.
will be examining the results of some experiments concerning astronomy. But before we do so,
here we go.
I would like to present 2 particular points that will have a huge bearing on all that follows. The first
one of them is I don't know
what
dick.
Would you think of a university or indeed the whole university system around the world, that deliberately never mentions to their science students 3 important experiments, simply because they completely contradict the present accepted orthodox views of our planetary system and
So we got our
astronomy.
Sounds
conspiracy
legit
here.
so far.
This is what has actually happened.
All right.
The second is a scenario that I would like you to think about. Imagine that you are in a small boat in the middle of a very large circular lake. Not far away is a very large liner, and it seems to be going around you regularly. You know how far away it is, and from the time it passes a light on the shore of the lake, you can work out that it is traveling at, say, 30 miles an hour.
Good luck.
But it dawns on you that it might be you traveling around the liner, and you cannot tell whether it is you circling the liner or the liner circling you.
Something tells me
There is an
scale
easy
is
way to
important
determine
here.
which of these 2 possibilities is correct.
Yeah.
All you have to do is to put your hand in the water.
Small,
If
far
you
away.
seem to be moving at about 30
far
miles
away.
an hour, then it is
Small,
you circling
far
round the
away.
liner. But if you are almost stationary, then it is the liner traveling around you at 30 miles an hour. Now that is a scenario that I would like you to bear in mind in this video.
It's going to go off the rails
All
now.
orthodox models of the planetary system have all the planets circling the sun in an anti-clockwise direction, as seen from our North Pole. And in addition, the Earth is spinning on its axis, also in an anti-clockwise direction. On its orbit around the sun, the Earth travels at 30 kilometers per second through the ether. In 1887, Michelson and Morley carried out an experiment to check this speed of the Earth through the ether. They passed light through 2 long arms, one in the direction of the Earth's travel and the other at right angles to it. The light traveling in the direction of the Earth's travel should have taken longer to return than that traveling at right angles to the Earth's direction of travel.
Interferometry.
To the amazement of the scientific world, no such speed as 30 kilometers per second was detected. But they did get speeds between 1 and 10 kilometers per second. Ignoring these speeds, this experiment is always referred to as giving a null result. This shook the scientific world, and to overcome the implication that the Earth was stationary, they invented the Fitzgerald-Lorentz contraction. This claimed that the arm that was in the direction of the Earth's travel became shorter.
Okay, do you want to stop it and talk about all this right now?
Sure, okay, sure.
As in the other.
I think we should. As a layman, I know how that this is God entirely bogus, but I don't have the elegance that our guest does. So please, sir.
So the Michelson-Morley experiment, they got it somewhat right, but they kind of missed on it. So the Michelson-Morley experiment was an attempt to try and understand Earth's motion in the cosmos. Right? It was at the time it was speculated that light was a wave propagating through a medium, right? And so if you were moving in that medium, like if you're moving on a lake, you could see the effect of those waves. And if, for example, if you have waves coming at you and you're heading in the direction of the waves come faster. And if you look in the backwards, the waves are receding slower, right? It's the motion relative to the waves that they were trying to experiment and trying to measure. So that was the original set. And the interferometer is a system whereby if you have light from a laser, it's a fairly stable frequency source that you bounce off of a stationary mirror, come back and combine, you'll find the light will either it will amplify and show a spot, or cancel and or somewhere in between, where it essentially the light coming backwards will cancel it. Now, if you start taking that mirror and start moving it, right? Let's say let's say you have a nice air track where the laser is bouncing off of a mirror that's moving. What the light that comes back has been you have a slightly different frequency, right? Because of the motion of the mirror. And so what'll end up being is, when you combine the original laser light and the reflected light, the things will go in and out of phase. It'll act sort of like a heartbeat. And so Michael Morley in that bounce with the they had actually, instead of a laser, they had a fairly narrow emission band of a particular material that had a very, very narrow peak. That's one of those physical chemistry things. So shining a very, very narrow wavelength of light, doing the bounce, combining it back, and seeing if they could detect motion. Right? If the apparatus is moving relative to the light source, then you would get this phase effect. If it's stationary, you wouldn't. And the actual experiment was actually floating in a ring of mercury, so that it dampened out effects. This is before the days where they had a really nice, stable optical tables, and but the ring of mercury could allow them. Excellent job, and you could rotate slowly the ring around, because imagine again that the hypothesis was that light's traveling is a disturbance in the medium. They called it the ether, and if the Earth is moving and you move in the direction the medium, you'll see the effects of that of light propagating through that medium, and you'd be able to tell the direction, the net effect of Earth, its spin, its orbit, all those sorts of things. And to their surprise, the expected effect and expected motion wasn't there. There wasn't even a preferred direction.
So the overall conclusion is ether, not today, not a thing. And interestingly, the interferometry principle is the same that's used in ring laser gyroscopes of the type that Bob Supernoodle used so compellingly to prove empirically that the Earth rotates at 15 degrees per hour. Anyone who is concerned about the speed of the Earth rotating, what I want you to do is at sundown, face west, watch the sunset, and tell me how fast 1,000 miles an hour looks like, because you're seeing 15 degrees per hour.
Well, I can tell you how fast
you can say you're what? It's really cool.
when one of the experiments we did at South Pole Station was we set up a Foucault pendulum. Now it was the Foucault pendulum.
You went to the South Pole?
Oh, I'm a frequent visitor there.
You're not allowed to go there because the military patrolled the
I'm
whole
a frequent visitor there,
South
and every time, in fact, one of my jobs when I go to an expedition is to find the South Pole within 1 centimeter. So that's about the size of a 6-pence piece, right? There.
I'm not worthy. I'm such a nerd.
and when we find the spot, then I conduct another experiment, which is, can I fall off? Does gravity still work? And so I do several attempts to see if I can fall off the Earth. As you can guess, I failed so far in all of my experiments, because it might be a time and everything. But within, I would say it's within about 200 meters or so. There's a stairwell that's enclosed that we had a 300 kilogram weight as part of a Foucault pendulum to start the swing, and it was a really nice result, because usually when you do the Foucault thing, you have to do like the cosine of the latitude variation, but this is the case where you're literally, the Earth is turning out from under it minus 1 day a day, right? And so you can see the drift of that Foucault pendulum at near the pole directly. So it's a kind of a fun little song. But back to think about the Michael and Morley experiment. What they said was, again, approaching it from a scientific perspective, they said either there is no ether or the Earth is stationary. It's effectively the layman's terms. And they rejected the Earth being stationary thing, if nothing else, because they know that at a minimum you can prove that it spins on its axis. But you can say, well, why not the entire universe spinning as a result, and Earth being in this perfect spot? Well, at that point, you've got to handle, well, then how does the Earth remain stationary, but the moons around Jupiter we were talking about spin on there? I mean, how does Earth become the only spot in the universe that's fixed, and everything else moves around?
God magic.
That's called special pleading.
God did that. God did it. I've heard.
I don't know. If I drink a lot, I feel like I'm pretty stationary, and the rest of the world is moving. So I'm just, so I don't know. I become the center of the universe when I get really hammered.
I mean, the alarm bell started going off talking about this hidden evidence, and the universes don't teach this stuff, right? This is information that is actually taught in the Michael and Morley experiment. I had to go and build a Michael and Morley interferometer myself. I wasn't allowed to use mercury baths because the vapor's kind of.
That's a bad idea.
It's kind of
health and safety.
Mercury vapor is bad. Mr. Mackey say mercury vapor is bad. Okay. But the thing that they found was that there wasn't an ether, right? Now we understand more now from Maxwell's equations is electromagnetic propagation, and it doesn't have to require an ether to go through the light can go through a vacuum perfectly fine. But they were looking for this motion in the ether, didn't find it. And they said, so how when you don't find it, what's your conclusion, right? They didn't find the motion they expected. They talk about the speed, right? The speed is because you can calculate the Earth's spin. You can measure its size, so your angular momentum. You should expect at least to see that motion in the ether. So let's talk about that speed they're expecting. Well, at a minimum, if you know the Earth's spin, you should be able to see that, right? And you should be able to see, when the sunrise, you should be going one direction, sunset the other, and you should see that disturbance going through the ether, and they didn't see that. Now, the reason comes down, they didn't understand, but now is one of the amazing results of relativity, which is the speed of light in a vacuum. Is the speed of light in a vacuum? Is the speed of light in a vacuum, and it is independent of observer in motion, right? Yeah. So the light they were measuring is going to come in and bounce around, always at the speed of light, and there's also not a propagation. It's going to cause the frequency to shift as well.
I always thought the speed of light was relative to the observer. It's the only thing that is the case of. So, we perceive the light from the Big Bang, for example, as we use that to calculate the distance to where that happened, for example. Because we know the speed of light in a vacuum is the speed of light in a vacuum. But we're at a point when we make that observation. If we were at a 90-degree angle to the line between what we're observing and us, out there, say, half the distance again, how fast would that light be perceived to be crossing our path if we could actually see it?
Well, particles that don't have rest mass can only go c, right? And c we call the speed of light, but to be fair, it's really the speed of causality, right? It's how fast cause and effect can occur. It's the maximum speed. So the 300, so that the 300,000 kilometers per second approximate, they talk about speed of light in a vacuum. Really, c is a propagation speed. Now, here's the thing: is that if you were, let's say you were able to travel half the speed of light, towards a source. And so you're looking at a star that's sending, so the star sees light leaving its surface at the speed of light, and you're traveling towards that star at half the speed of light. What's the speed that the photons reach you? Right? What's the speed at which they come in and strike your detector? It turns out to be the speed of light. It doesn't matter how fast you're going relative to your surroundings. The speed C is always C, right? And so, well, how could that be? Because you would think, well, if I've got one C coming at me and I'm half C going this direction, wouldn't I see the things hitting me at 1.5 C? I mean, that would be the Newtonian aspect. That was what Galileo's principle would say. But it turns out, no matter how fast you're going, those photons arrive at your detector at C if they're going through a vacuum. Right.
Same thing. Sorry, it's very fascinating. As we're going into from Newton to Einstein and ultimately perhaps to Hawking, I've had people deny space-time as a thing when I've pointed out time dilation as a function of gravitational fields and gravitational lensing. Could you jump into those concepts? Because I find them to be a physical manifestation of the concept of a space-time continuum. Blessings be to start.
Because part of this business is that I think one of the things that we Einstein brought forward is Newton would have said gravity is a force. You say, well, force for what?
You can
right?
observe
What's
it,
going on here?
And
you can treat it as a force to get pretty good results. But what Einstein said is that gravity is a distortion of space-time. This grid of the fabric of space and the propagation of causality, time, it mass distorts the space-time, and space-time distorts how mass moves or how light moves on its straight lines. So when we see light,
is the rubber sheet example maybe a useful thing?
If
you hold a rubber,
so.
Yeah.
Go ahead.
Yeah, if you, I found it a useful way to visualize this. Space-time, we're talking about a multi-dimensional matrix, but if you break it down into the 3 dimensions we're able to contemplate easily, the space-time matrix could be described as a flexible sheet. You hold it out at 4 points, you put an enormously heavy weight into it, and it will deform that sheet. The deformation is the visualization of gravity, the effect that we see. Essentially, and as a biochemist, I like to be able to use Lego really to work things out rather than sums.
I use Legos all the time for stuff like that, particularly when you talk about boiling points and molecules. How well will they stick together? Is there enough surface area? What kind of intermolecular forces are at play?
I've found that trying to discuss 4-dimensional concepts like the tesseract and things with people from 1940 isn't really the best thing. So the rubbery sheet is a good image for me.
Yeah.
And having done this,
it's a good way to sort of try to visualize, like by cutting out some of the dimensions and bringing it into something which is there. Now it has its issues, but I think the analogy is there to give you a hint of what's going on in the Lorentz transformation is correct. But one of the things as well is that, for example, the principle of C being constant and independent of the motion of the observer is fundamental within relativity, and that has some profound effects. So let's go back to that business of let's say you're a spaceship traveling at half the speed of light, and you turn on your headlights, right? Your high beams. You will measure light. Let's assume it's a vacuum, right? Leaving your spaceship at the speed of light. An observer watching you approach at half speed of light will observe light from your headlights reaching them at the speed of light. How could that be? If you're going half speed of light and something launching from you at 1 speed of light, wouldn't it strike the observer at 1.5? Answer is no. Because one of the things that starts happening when you start traveling at lower relativistic speeds, the things you think that are constant, like the flow of time and the grid of space, start warping, right? And so if you feel, what happens is that the geometry transformations have a distortion such that that distance and that time get distorted so that the light will leave you, because you perceive yourself as being stationary, right? You don't see motion of yourself, right?
Right.
And you see light moving at sea. The person who's seeing your head beams, come at them, see it right there at sea. Now, what they will see is they'll see a frequency shift, but that's also again to the time effect. So what happens when you encounter when something encounters, for example, a strong gravitational field, the rate of time slows down. Right. And this is not just a trick. I mean, we are seeing this right now with a Parker space probe. There's a probe that's in a high elliptical orbit, and it dives in near the sun and comes back out. Where the main part of the probe is to understand the amazing corona and the physics going on there.
Yeah.
But on that probe is a very accurate clock.
Also, the reason that our GPS works depends upon understanding the difference in time at the satellite level from here. Again, I've had flat earthers saying, you just said this happens. No, we're not guessing. This is a measurable,
we're actually measuring,
fantastically measurable
thing. Gets close, it's now within inside Mercury's orbit, and it comes back around. Its last top speed that it ran at was 212,000 kilometers an hour, right? So that's getting to the point where it's not it's not 300,000 kilometers a second. 212,000 kilometers an hour is a really amazing speed. And one of the things that happens is that as that probe comes in towards the sun and experiences stronger gravitational field, and also do its motion, time for it relative to us slows down. So it has this accurate clock that goes beep, 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 goes in, dives into the sun, comes back out. We do a clock sync against, and we find its clock has lost time relative to us, right? In fact, we have to go and tell it what the new time is, because for it doesn't see this slowdown. It says, no, your clocks are fast. And we say your clocks are slow. So to be able to do the synchronization, we have to fix that sort of stuff. This is stuff we directly measure.
It's beautiful. I mean, throughout my adult life, gravity has become or has been defined as a thing that influences matter, a thing that influences time, which is very well understood, and now a thing that influences light. Could you reach into gravitational lensing and why that concept vindicates to an extent the thick end of relativity?
I mean, because one of the things that amazing thing about gravitational lensing is that if you have a distant light source, and between you and light source within a line, you have a mass, right? That mass is going to warp space-time. So the photons, rather than doing a straight path towards you, can't, because they'll be bent, right? So what happens is so here's the mass in between us, right? You're the light source, I'm the light. The light that reaches you actually doesn't go straight to you. It's got to basically bend around this because the mass is causing the straight line that the light sees actually, from our point of view, curves around the mass. So in order for you to see the photon from me, what you're seeing is light coming off the side that's being bent and focused on you. So it really is
the momentum, though. Yeah.
The light is going around and coming back in. Now, if this light source is very far away and is very diffuse, well, you've got a mass between you and it that allows the light to be focused. then not only do we can you detect it what otherwise would be too faint, but you also see this because these are arcs or rings that become how aligned it is with you. And so we detect these arcs and rings all the time up in space for very different distant object, let's say a quasar, with light coming from it that's passing by. It could be a black hole, it could be a cluster, a faint cluster of galaxies, whatever, but the space is warped, and those and all those lines eventually come around. So it's not the straight point source you see, it becomes this collection of arcs that pass around it and come back and focus on your spot. That's essentially the amazing stuff with these gravitational arcs and rings that Einstein predicted should be there, but thought they would be too subtle to observe, and he was right at the time. And of 1915, 1916, they were too subtle, but our detectors have become good enough that we can actually detect them now on a regular basis. But again, people say, well, what do you mean that this you're invoking all these weird stuff to explain all these arcs there? If you want to see curvature, measure curvature, look at this object, right? I throw it up, right? It comes back down. Why? Ask yourself, why does this object go up and come back down? Right?
Magic? Jesus.
Goblins? And it has nothing to do with density, right? So imagine, because I can't do it given the scale of things, but imagine I have something where I'm going to throw an object up. It'll take 1 second. So kind of 1 second, it stops, hangs, and comes back down and falls back down, right? So 1 second up, 1 second down, right? And we know from the typical gravitational field near the Earth, 9.8 meters per second squared. That's 4.9 seconds up, 4.9 meters up, 4.9 meters down. And you say, well, what's happening? Why does it go up and down? Why doesn't it just launch and go straight up? Well, the answer is space is curved. What do you mean space is curved? Well, that's why it's going up and down. Oh, well, how do you measure the curve? Well, if you were to draw a graph, right? So let's draw a graph, and on the you talk about the height, right? You would see this nice. Let's say that the x-axis is time, so we have 2 seconds, 1 second up, 1 second down, right? And the y-axis is distance, right? You get this nice parabola, right? It's the old cannonball effect. You launch, go up and back down. You'd see that arc.
Why add physics to throw pointy things at people?
Yes, because physicists were the bored people in the back of the room trying to rationalize disturbing the class as an experiment.
Come on, lads, let's blow some shit up. We can hit them right over there. It'd be great.
Oh my goodness.
So now let's take that. So you got the notion of that graph, right? 2 seconds on the x-axis, 4.9 meters up, with that nice parabolic arc. You're seeing the curvature of space. You say, but that doesn't make sense. So let me help you you need to have a XY graph with the same units. You can't have 2 seconds of X and let's say 4.9 meters of Y. You want to turn the X into distance. Well, how do we turn time into distance? Well, C.
Yes.
That's
light.
C, that speed of light in a vacuum. So that graph of 4.9 meters, right? C is 300 million meters per second. So if I have 2 seconds, I have 600 million meters. So now you need to scale the graph right. You can't just distort it. So your scaled graph of that object of the ball going up for 1 second and coming back down needs to be 4.9 meters high and 300 million meters long.
Mm-hmm.
Right? That arc, that line is going to reach up to the top and come back down. But that size of that graph is going to be 600 million this way and only 4.9 that way. That line is not a straight line. It's slightly curved. Otherwise, it wouldn't get up to the top and back down. That's the curvature of space-time here on Earth. That's how you measure and can see space-time curvature here on Earth. You don't have to be doing some relativistic thing or going around the sun or flinging yourself around Jupiter or other things. You can just take, go next time you go to a sports stadium, cricket, soccer, baseball or something, and see them going an arc, you start to say, see there's space-time being curved.
We have
Exactly.
2 more things left to do on the show.
Okay.
First, we have a new commercial from our latest sponsor. I think you'll appreciate this, which kind of leads into, yes.
I need to ask a fanboy question. I'm not worthy, and I'm in awe. Would you be willing to have a short conversation with me at your convenience about theoretical warp drives? Because
yes, we could actually have a sane discussion about that. You can actually have a mathematical discussion about warp and fastness and speed of light stuff.
I love it.
You have to talk about it in terms of theory, not because we don't have reality yet and we don't know how to do it. But yes, you can have a sane discussion about stuff like that.
Thank you. On with the absurdity on the internet. And have a conversation with an actual scientist about warp drive. I'm alive at the right time. Oh.
But just spoiler alert, I don't know how to do it, but that's
okay.
No,
That's
well,
okay.
we didn't know how to build airplanes for a long time, but we've got that down. So
and then rockets came after that, so that was nice. Yeah.
Yes.
Yeah. Cool. So we have a commercial from our latest sponsor, and then we have stupid things after that.
Cool.
Because why not? so let's have a look at our latest commercial from our latest sponsor, who's
otherwise known as the religion segment.
Hello there. You might remember me from my previous commercial called Bigfoot Believe.
Cool.
We are an organization that...
Cool. You have to check the folder. It's a newer one.
Mel, is that you with a beard? Because that's not a good look for you.
Maybe. I uploaded a new one. It's called JourneyComm.po4. That's not me. Well, it is me, but it's an animated version, and that is my voice. And this is totally not real. If I was a dude that had a beard and blue eyes and animated and a floating head.
Why are you doing this to yourself, Mel? I mean, you've got a perfectly good talking head here. You need a rude Scottish guy to insult people, abuse the faithful, or defame the masses. Just bring it on.
There you go.
There. See, that's more of a digital version.
I am the digital representation of ScientistMel. I want to take a moment to thank all of my patrons on patreon.com/ScientistMel, as well as all of you who are giving through super chats and my help with GoFundMe for my computer. Thank you so much, as well as PayPal and any Streamlabs donations. I really appreciate your help. So guess what, guys? We have a special word from our newest sponsor. So let's check it out. Yay!
Give Mel your money.
You might remember me from my previous commercial called Bigfoot Believe. We are an organization that naturally and without the use of chemicals removes all kind of cryptids from your particular property. Well, guess what? We are now offering new travel services. Our latest service that we're providing is an expedition to the top of the world to enter inside a hollow earth. Have you heard of hollow earth? There's lots of movies about it and a book that was written called Journey to the Center of the Earth. If it's written down somewhere, that makes it true. So,
I live near the entrance.
Join us on our travel adventure to go inside the earth and see wonders that defy science. There are multiple packages available For those of you who just want to travel to the top of the world and see what that looks like, that's fine. For those of you who want to travel along with us and go inside of the Earth, you're going to have to fill out some liability forms because we can't guarantee that the humanoid lizard people won't attack you. And insurance options are available in case that happens. Our tour guides are fully informed and will be able to express with you all of the information associated with Hollow Earth about what it looks like, the humanoid lizard people, the dinosaurs.
That's
and
your
we'll also
boyfriend,
have
Mel.
the movies available to help you educate yourselves as well as to what to expect as we journey to the center of the Earth. Check out our website and sign up for the trip there, or call us at 555 Bigfoot. That's 555 Bigfoot. Packages start at just $3,000. That's a heck of a cheap buy, particularly when you're going to go see the center of the Earth. Go to BigfootBelieve.com for more information today.
I've been to the North Pole as well as the South Pole. Though they seem to be the top of the Earth stuff. Although didn't they show the Antarctica regime area? But people in the Southern Hemisphere would claim that top of the Earth is one of those hemitheorist dispute thing, right? But yeah, so I'm bipolar. I've been to both the North and South. However, if you go to the center, there'd be so many great experiments I'd wanted to do just in terms of measuring the material down there and understanding why Earth's core rotates at a slightly different rate than its crust. And the difference between the core rate rotation and the crust rotation is about 1 degree per century, right? So that's it. That doesn't seem like a lot, but in terms of 36,000 years for a complete flip, that's actually a pretty high velocity, and one of the things that probably changes the physical properties. Because we think that the given seismic, waves that go through the Earth, which is how we tell it's not hollow, those waves, we have a solid core and a liquid material surrounding a solid core, which is probably where a lot of the origin of Earth's magnetic field comes from. But I had when I had several years ago, they did I did open heart surgery on me and repaired my mitral valve, and
well done. Congratulations.
I'm still here ticking, yay! But the anesthesiologist, because I was known as that's the Pluto guy. He likes to talk about Pluto and all the astronomy things. And so the anesthesiologist came in and started talking to me, and he said, "I understand an astronomer." It says, "I have a question." He said, and it's a serious question. How would you prove that the moon was not hollow? I didn't claim it was. He said, how would you prove to somebody the moon was not hollow? And so we went through these thought experiments of what you could do to show the moon was solid and not hollow. And those similar things could be done on Earth, but it's a bit hard, more challenging to do it on the moon. And then about 35 minutes to this thing, we were going back and forth, and I was actually encouraging him to go and get like a whiteboard. We could start doing some equations on it. The surgeon calls in and says, "Where is the patient?" He says, "Well, he's still here chatting away. Mm-hmm. We gave him the stuff he's supposed to
still conscious.
Go out." And so they gave you another dose. And by the way, that's when the assistant anesthesiologist said, "I understand you do stuff about prime numbers." We started talking about primality testing as I literally was wheeled into the room, and we had another half-hour conversation before they give me a third one. So don't get a scientist started because we get kind of excited and we forget to do things like deal with anesthesia. So
yes,
but quickly, but think about that for the audience. How would you prove the Earth is hollow or not hollow, or how would you prove the moon? That's even harder. Is either hollow or solid. What would you do to go about? What's your experiment? This is a scientific method of saying you don't make a claim. You
Right.
see, science is about questions, right? Science values questions. If you get a result, it's merely a stepping stone to ask more questions. Science values
And
scientists who can ask questions. If you want, quote, answers, then you're interested in dogma. Go talk to your local religious something, whatever. But science is about questions. And so that question about how would I determine whether the earth was solid or hollow inside, and go through those experiments, and you can actually then on Earth you can actually conduct those experiments. On the moon, we can take data we've taken from it and also do some observations here to infer that the moon isn't hollow. But
there's
do the
another
experiments.
nuance of the another nuance of the scientific method that I think is often lost, unfortunately. It's also not about being right. It's
Oh
about
God.
d-
Right.
it's about forming a hypothesis that's consistent with reality, with everything that we
Yes.
see. So way back in my career where I was a real scientist, I published a paper in a review journal that was a position on this field. And I synthesized a model that I thought, I was convinced wasn't accurate, but it was consistent with everything that we knew, and published it saying, this is speculative. This model is consistent with everything that we know, and here are all of your papers, but I think I'm wrong. More positive reviews of that as a stimulus to new questions than if I had published it saying, this is what I think's happening, this is what's going on.
It really is, and that's really important part of the process. You know, the making it more nuanced to talk about the null hypothesis and failing to prove the null hypothesis. But effectively, you know, your science is about questioning. So at the beginning of that video that they showed about the hidden evidence and stuff they want you to know, that's not that's actually not what happens, right? It well, first of all, it's not hidden because he's explaining it, but secondly, you know, the questioning again is all about that. So why did I repeatedly measure the speed of light in a vacuum in college, and why did I go about trying to measure the curvature of the Earth and the mass of the Earth and the distance to the sun, so forth there? Because this is part of the asking questions things, and if you get a result that may or may not agree with your model, but understand that the universe doesn't ask your permission to do what it does. So your model, you can have all this mathematical model, all this great stuff there, then the universe doesn't really care what it is. Your job is to try to model the universe, not the universe conform to your dogma, right? So again,
I mean,
you know,
didn't the Copernican model suffice for several centuries?
except of course the you know, the Copernican model, and when actually you did the measurement, the circular orbits that Copernicus had in his model produced a worse result in terms of predicting the position of planets than Ptolemy's model.
Right? Yeah, apologies for the audience. The Ptolemaic model predates, that goes back how long? At least a millennium and a half, I think.
It's probably yes, a minimum. You know, it's at least like maybe 1800 years, 1900 years, somewhere on that order.
Yeah,
but again,
that worked adequately for an extended period, and then it was updated because that's what science does. And yeah, that wasn't correct, or at least our model now is more correct with more predictable properties.
Very accurate building of positions of planets, and actually doing cartography, right? Like the surveying, but surveying the heavens as opposed to drawing fantastical lizards up in the sky, right? And then very accurately measuring. His visual acuity was extraordinary. And then Kepler used Tycho's data and added his own height because Kepler was one of the few people that could do observational acuity to the level that Tycho, and that's how he became his assistant. And then Kepler, looking for a simple model, kept trying to come up with these spherical, circular shape things. And finally, when
it's logical. It makes sense. aesthetically,
because he was trying
it's
to
like,
find
it's
this
a circle.
rationality. But what Kepler did was said, well, ellipses actually do an extraordinary job of predicting the motion, and furthermore, the Kepler's laws are things we use because this guy named Isaac Newton, using calculus, explained that an inverse squared field, what we call the gravity field, produces orbits that are elliptical in nature, not circular. And so Kepler was able to predict, and explain why, for example, and in fact, the not only are the ellipses, but they're also not in line. Everyone wanted this nice, flat, clean universe that they usually would bring God in to say it's got to be perfect, and God wouldn't, sort of thing. And now we know that yeah, things are in ellipses, and in fact, that worked for a while, as you said, until we started looking very carefully at the orbit of Mercury and find that ellipse wasn't quite going the way Newton expected it to be. And it wasn't until Einstein relativity that we found things like relativistic precession, right? And so people keep asking this question. So why do we keep measuring this stuff? Because science is about asking questions. It's not about answers. If you get a result, it's merely the stepping stone to ask more questions. So we're asking questions about what are the composition of atmospheres of planets around other stars, and do they have interesting chemistry, and is that chemistry similar to us or different? And we'll get some results. That's not where you stop. Those results are merely stepping stones to ask more questions. So I would encourage the audience, keep asking questions, because that's scientific.
For any parents or teachers in the audience, the most powerful answer you can give, in my opinion, in response to the question, how does that work, is, I don't know, let's find out.
Yeah.
Yes.
Exactly.
That's what
I agree with
that's
that.
what my parents did when I was asking them ridiculous science questions. I don't
And
know.
someone asks,
what
so when someone says, examples, and usually is one of the you're in a taxi and someone says, well, you're an astronomer, blah, blah. One of the questions you get asked is, do you believe in extraterrestrials? And I usually, I try to make it that teaching moment and say, why would what I believe have any bearing on whether there's life outside the Earth or not? Why would you want? I said, perhaps maybe what you should ask is, would I find that we were alone in the universe as the only place for life? Would I find that result surprising? And the answer is yes. And you say, the next question you say is why? And you produce this data, and then you ask questions about that and questions about that, and pretty soon, you're deep in the scientific method. Don't ask someone, do you believe in the flat Earth, or if the Earth's stationary? Ask questions, do the experiments, and continue asking questions.
I like to break that down into, are you asking, is there life in life, and or will we ever encounter it? And is there life? Almost certainly. Is there intelligent life other than those on Earth? Almost certainly. At some time, some place, will we ever encounter it? Based on the bigness? Almost certainly not. Probabilities just break down after a certain point. And imagine life popping up like the flames in a fire on a cosmic scale. We're here and we're gone. A whole civilization, a whole biosphere, a whole planet, here and gone. You may have the occasional one that, but I'm pretty hopeful about you.
With multiple variables after a period of time, you can't predict beyond a certain point. I mean, we have chaos theory for that. We have just one more segment left and only a handful of minutes. So
I'm real hopeful about you. I'm real hopeful about Europa. Jellyfish.
We'll have to call them Europeans, according to Neil deGrasse Tyson.
and then as the final thing you said, back when you just one little minor point on there with that video and talk about this hidden evidence and stuff that's held from you. That's not scientific method. Science encourages students to question and to question and to question and to question, right? And the notion that science is somehow conspired so that stuff isn't talked about, that's not scientific. Science questions. So you're interested in relativity, ask questions, challenge it, and
Yeah.
test it. And guess what? If you were to find that people's models have an error, you would become an extraordinary scientist like Einstein.
Okay.
So it's worth asking questions.
So-
Question.
And the image that I have is Lieutenant Data, Stephen Hawking, Einstein, and Newton playing poker around a table. You can join that storied number if you can, even point out to me the problems in the models that you reject. I'll have a science conversation with anybody, but if you reject reality as a starting point, I'll be washing my hair forever.
It says, rather than reject the model, put it in the form of a question that we can discuss.
Fair enough.
Jesus.
Oh God. Yeah. So we only have about a handful of minutes left. So we gotta do at least one stupid thing. It's okay. It's been invigorating and intellectually stimulating and a lot of fun. So Bull, we have the audacity.
You got the audacity. You're going to jail. You got the audacity. My name is Gina. You got the audacity. That's all I got to say. You got the audacity. I stole $3,000. You got the audacity. You got the audacity. Because you don't got no evidence. My name is Gina. My name is Gina.
You don't got no evidence.
You ain't got no evidence. So this I came across recently. This is from somebody named Rivellino, who gives lots and lots of advice on how to woo a woman or make a woman stay with you.
Great.
He basically says, never say I love you first. A woman wants to feel like she has to overcome obstacles to win a man's heart. The man who gives his emotional world away too easily robs her of the satisfaction of earning his love. Though you may be in love with her, don't say it before she has. So that's step number one. I'm not going to read all of these. Y'all can find him later on Twitter if you want and express your personal opinions.
Yeah, if you want to give up your soul to this.
Oh God. He says, make her jealous, flirt with other women in front of her. Don't dissuade other women from flirting with you. Women will never admit this. Jealousy excites them.
This man has never dated anyone from Scotland. Don't do that because you'll get punched in the face by her.
Always keep. Yeah. Another one is always keep two in the kitty. It builds confidence and encourages boldness with women. If there is another woman, a safety net to catch you in case you slip. Knowing there's another you can turn to for affection will fortify your will and satisfy your manhood.
Because women are entirely interchangeable. Everyone knows that. They're like socks, basically. Always keep an extra pair in the handbag. Ignore her beauty.
That's right. You
don't
need that.
Don't stare at her boobs.
I wonder about this person's interpersonal skills, if that's what it is the way of stuff. And the question, of course, is how many times has this person complained when this has been done to them?
Mm-hmm.
I know. He actually has a website, and it's way worse. It's way worse than this.
Did you ever see the film Magnolia, where Tom Cruise is like the jock, douchebag, misogynist, motivational speaker? And it's like, this man has no female friends, nor will he ever have. I'm not really sold on this, but then I've been single for the last 47 years. So what do I know?
That's okay. Another thing I want to show you guys really quickly. Did you know, Doc, that you can yoga away the flu?
Really? Imagine. Let's find out about this. Because I've been.
What do the viruses do when you're yogaing? They just like say, "Oh, this person really do yoga. Let's just
pull up the video that says yoga immunity."
They get sucked into the big squishy Pilates ball. That's what that does.
Welcome to Yoga.
Okay.
Immune support.
Be certain to turn it up a little bit.
Flu-proof.
So flu-proof yoga, guys.
Take
Here we go.
notes.
With your spine nice and tall, take a moment to settle into your body. Inhale
it's raining
deeply
there, right?
from the sacrum to the crown of the head. And
Yeah, sit
then
in the rain.
exhale all the way
Yeah, she's gonna
down.
get pneumonia.
Interlace your fingers and start tapping your palms
doing it.
into
I'm
one
doing it now.
another as you create a reverberation through your hands. Inhale
This is
and
foolproof.
exhale.
Yeah, it's really important to keep doing that.
And do it in the
Gently
rain.
begin
You
to
know, I don't know
tap
what they're
into
doing.
your sternum and the
Oh, here
upper
we go.
chest with
Right.
your hands
Into chest.
interlaced and your
Om
knuckles
Shanti
and your
Shanti.
thumbs moving into the chest, stimulating the
Right.
thymus gland.
No.
Keep on
doesn't.
tapping.
That doesn't want. That doesn't. That's
Keep
not
your
how it works.
fingers
This is squishy
interlaced.
bio
Relax your shoulders.
and stuff. With mixed with a bunch of woo.
Tell us about the viruses. Come on.
And insert your thumbs under your collarbones.
Your ass.
Begin to circle clockwise, stimulating
Okay.
the
Clockwise.
thymus
One more
gland
thing.
again.
Clockwise relative
Oh,
to who?
God.
To
Yeah, it's
to
re-
the
The pressure.
to the observer or to you?
Don't ask. It's really important that it's clockwise relative
Open
to crown
and slide
chakra.
your thumbs
Oh my
under your
God.
armpits.
like-
Interlace your fingers at the front of your sternum.
you
Exhale and
sniff
contract.
your
Inhale,
fingers
lift
later.
your elbows.
Hang on.
Lift your gaze.
And you see if you
Wrap
see it.
your hands around your neck. Exhale and contract. Inhale, lift your elbows. Back bend, elbows point
Don't
up.
What's this?
squeeze your neck too hard though,
Exhale,
because that breathing
contract.
thing might be interrupted.
Inhale,
All right. One
reach
more thing
up.
I got to show you guys.
Reversing
The other
the
video
flow
called
of
You see the
breath.
viruses
ASMR,
just being
Follow Earth.
destroyed.
Yeah.
Yeah, they're just
Can I do an infectious disease moment here?
Sure.
There are diseases I worry about and diseases I don't. Ebola is not a disease I worry about in a global sense. Flu is,
Mhm.
because there will be another pandemic, and you know, based on the numbers, somewhere between 200 and 300 million people might pop their clogs. And it's really nasty, and you should get your vaccines every year if you have any contact with old people or young people or people generally.
Or if you travel,
It's not
right?
perfect.
I mean,
Yeah.
the traveling thing, like
Sorry.
I'm going to the alleged continent of Australia in a week or so. I say alleged because again, that's a
Well,
flat joke.
it's to the northeast of Russia, apparently.
and again, having that vaccine, but is the next flu pandemic just a matter of time? And is as more people as let's say if vaccinations for flus improve, that doesn't eliminate the possibility of a flu pandemic, does it? It just reduces.
No, it doesn't. No,
Yeah.
there are a couple of factors here. The first is really why the vaccine is not perfect, nor can it be perfect. Flu, for a couple of reasons, makes copies of itself very poorly. So the concept of a pure strain, a fixed immunological target, is meaningless. It also recombines between species, so it jumps in evolutionary senses. And in terms of the pandemic, yeah, it's absolutely inevitable. We had one with swine flu, which was fiercely infectious, but not particularly pathogenic. When you get one that's fiercely infectious and pathogenic, then it burns through the population. The key to the vaccine is, although it's not 100% for any flu strain, it's some percentage for many of them. And you build up a repertoire of immunity by getting similar but not identical vaccines. So an issue with the 1900s, 1916 flu pandemic was older people survived, typically, and people in young, good health died, typically, because older people had been exposed to similar strains previously and had acquired immunity to them. But the others don't. And I've been involved in emergency planning for these kind of things. And basically, in an industrialized nation, first world, all the benefits of resources, if you lose 30% of your population through incapacity or death, your infrastructure is gone. within about 3
significant
weeks.
economic impact as well as social impact on stuff. Yes.
Yeah. I mean, at that point,
Well,
there are no people to bury the dead. There are no nurses. There are no cops, and so on.
Right.
so if you've and unfortunately,
We can't hear you,
I think
Doc.
when he knocked his mic off, he also knocked off his sound.
Can't
No
hear you,
sound.
dude.
So because I was going to ask him, saying, well, all right. So the next really nasty pathogenic flu bug comes around. What do you do about it? Well, and you could say, well, preventive measure is become immunized to a wide strain so that it reduces its chance of affecting you. But what else can you do? So let's say that a really bad flu outbreak, and it's a species jump, it's mutating, it's pathogenic, it's a nasty one. What do we do? What's the
We can't hear you, Doc.
when you knocked over your microphone? When you knocked over your microphone, you cut off your sound.
Yeah, unplug something.
You killed it.
There you go. Now nope.
No.
Nope, that was me, Landon.
Nope.
That was me.
No, still can't hear you, Doc. So, well, it's almost time to wrap up anyway, because we're around 2 hours, and I know Bull has to get ready for the geek room here in a bit. Maybe I think Doc is probably going to refresh or something.
Yeah.
But
So I wanted to know what they do for this pandemic thing. So we logged in.
You know what?
Hello.
I will.
Hello.
Oh, there you are. Okay.
Can you
Answer
hear me?
quickly, Doc. Yes.
Yeah.
What can we do in this pandemic?
Get your vaccine. Wash your hands. Eat your dinner, and stay away from sick people. If necessary, wear an N95 mask and wash your hands again, especially before you have any contact with the elderly or old or kids, because those are the ones that get knocked off by that usually. And if you are at the point where you're very seriously ill, go to hospital and they'll give you fluids and, if necessary, horrible antiviral drugs that can help. But yeah, flu is a disease that kills people every year, and it's horrible, and it's one that I think about quite a lot.
And the problem is that when the pandemic starts, the best thing they can do is add that to the flu vaccine cocktail for next year to try and. But when it starts, it's already too late, and you just have to be preventative.
So every flu culture is different from every other one, and the change is generally slow, but not always slow, and it's restricted by certain functional requirements for the two primary antigens. But every year, myself and a bunch of other guys get together and decide what those antigens are based on what's happening in the world and what we know about evolution, and we make a pretty damn good guess. But from inception to final vialing and administration, you're talking about 8 months fastest to generate a complex vaccine of that type. That's not an easy thing to do. Yeah. So one of the things I'm looking at is shotgun vaccine development, where you can actually do it per outbreak. We're a long way from doing that, but you do it per outbreak. You do it very much case specifically. And then instead of having people with flu wandering around hospitals and whatever, you isolate that outbreak, you treat those, and you vaccinate everyone around it. It's like a fire break in immunological terms. But we're a long way away from being able to do that properly. But vaccines against other stuff like cancer, we're getting better at that. Pretty cool.
Well, best wishes to all of us. We're going to need it.
Absolutely. We have to kind of wrap up now, but this has been amazing. Would you like to be back sometime, Landon? And we could maybe talk about Star Trek stuff, warp drive, what's possible, what's not. I know Doc is a game.
And I can talk about the astronomical equivalent, which is a the asteroid headed our way And what do you do about that? There's
Yeah.
That would be awesome.
you don't vaccinate
We would love
yourself,
to
but
have you. So.
there's thing about what do we do to make sure that the next asteroid, and there is a next asteroid that has our number on it, we can potentially do something about it.
It's very much the same kind of concept. It's like, this will happen, and it might not be for a very, very long time, but this is a probability of 1 overall, or damn close to 1, tends to 1.
Yeah.
Awesome.
And the other answer is that the what you think obvious question or obvious response, like blowing it up, isn't the actual answer, and we can discuss why. Much like you say, when a pandemic doesn't vaccinate everyone and everyone stops.
Armageddon,
Right?
the film, they didn't get that right. Bruce Willis film
a
isn't
little bit
correct.
of physics problems there. But yes, I'd love to come back there.
Awesome.
It has been a delight. I've really enjoyed
it. Stuff and a little fun stuff. But leave us please consider supporting content creators like this. You saw the ad, but if this is something you enjoy, the way you can be sure that you have more stuff like this you can enjoy is to support them, right? And they have all these support things you can do.
We have a lot of science people that come on. We've had Dr. Leah Torres to talk about reproductive rights, as she's a OBGYN. We've had we've had Arn Ron here. We had Bill Ludlow at one time before he passed. He was on here discussing that. Yes, we have Dr. Amanda Glaze coming up. We've had PZ Myers on here, but Dr. Amanda Glaze does evolution, education, and overcoming that cultural pushback that comes with trying to accept that. So we do a lot of stuff here, and even though we're kind of tongue in cheek and tell a lot of jokes, a lot of people are they're benefiting from that. So yes, please like, share, and subscribe. Thank you for being on the show.
Do you have like any other things that if people wanted to contribute to, do you have like a Patreon thing or other stuff?
I do. I have patreon.com/ScientistMel. I have a website where I post all of the slides. I have a Saturday show that I do that's exclusively science, where it's all viewer generated for topics. They tell me what they want me to talk about. I get together a little talk, and we have interactive stuff. All of my sources are on my website. I write articles. I generate content for teachers. You can support me through Streamlabs. I have a PayPal, patreon.com, all of that. And so, yeah. Thank you so much.
And please, support these content. Go ahead.
I do none of that because I'm a big pharma shill, presently involved in makeup, whatever you want.
So if this is content that you like, please support the content creators that because they really need it, and that's how you can ensure to get more stuff like this. And also, please continue to ask questions because it's very fundamental to the scientific method. And please continue to enjoy my favorite universe.
Thank you so much. And do you have a YouTube channel? I wasn't able to find one right away. I don't know if you do anything like
no,
that.
in fact, as interesting enough, I have a lifetime ban from YouTube because I made a joke in a chat room. I have a good friend of mine that lives in Australia, and I made a joke, making jokes about Australia being the alleged continent, and they deemed that to be potentially offensive to Australians. But because I never uploaded a content video, I can't get a community strike. You could get a community strike, right? Or that's where you get put in a timeout or that sort of thing, or have these stuff demonetized. I never uploaded any content. I never had created any content. So anything they do for me is terminate stuff. So
that's amazing.
I mean, talk on our show. That's fine. I'm fine with that.
Their algorithm.
Twitter. Go ahead.
Their algorithm has clearly never been to Australia. It takes a great deal more than that to offend an Australian, in my experience.
Yeah, I mean, there are certain things you can talk about that will offend an Australian, but that's not one of them. So anyway, so Landon Noll, Landon Noll on Twitter. I tweet, retweet lots of science things. Although they put out a few art stuff in there as well. And you can read about me. Go on to Wikipedia, Landon CURT middle name, NOLL last name. And
Can we
have
put
links to
that
my
link in
webpage.
the description?
I can do
Cool.
that. I'll put
Yeah,
all of
I
those
think
links
that
so
in
you
would
the
can
be
put
description.
my Twitter feed. As I say, I will. You get mostly sciencey bits, a little bit of art sprinkled in on top of that, and my webpage, a little bit of background on me, and of course Wikipedia.
I will add those links to the description so you guys can go check out the work that he does.
Yeah, I'm really looking forward
And
to
as
that.
it's been a pleasure, and again, please continue to enjoy my favorite universe of all the universes I've studied. This one's definitely my favorite.
Well,
Very
thank
good.
you again. So, any
Yeah.
any last thoughts, Doc Savage, before we sign off?
Yeah, very briefly for once for me. It's been an absolute privilege and a really exciting discussion. I hope it leads to many more. And thank you so much for sharing your time with us.
You're welcome. Thank you kindly. Let's do this again.
Thank you so much. And thank you guys for watching this episode of Oral Audacity. We will see you next week with Tony Reed. And then the following, we will have Dr. Amanda Glaze.
Yeah. Take care, folks.
Yeah. Yeah.
Bye. I absolutely adore Doc.
Because I have testicles for some reason.